Hey guys, welcome back. So this is the lecture for lab experiment 6. This lab is actually due a lot later, but I wanted to make sure that we went ahead and did this. This was really the only place that I could put it in the schedule. This goes with the gas laws. So there are things about this reaction that take us into the gas laws. So I wanted to make sure that we had some time to talk about that. So this experiment itself is going to be due in Alex. I think next week. I'm pretty sure it's the 11th. Yeah, virtual lab 6 is due on the 11th, as is the post lab for that. So make sure that we get all that together. I've also moved the reactions. Virtual lab 8 is that same day, due the same day. So we'll talk about that too. So that is what we've got there. Now, I really need to talk about the fact that this is based off of a lab that we do in the physical laboratory, because there are things about this particular lab that you probably will see on the final that are slightly different than what we've done in what is actually going to be done in the virtual lab. So we need to look at the lab manual and talk a little bit about how that lab is performed so that we can talk about what this looks like. So this is based on 5, which is stoichiometry, the gas evolution reaction. And what we're actually doing is the net of this. We end up forming the H2CO3, which spontaneously decomposes to H2O and CO2. So this reaction makes that happen. Okay. And we also form NABR, which is what we collect to be able to see how well this went. Okay. So we can calculate using the mass of the Na2CO3 that we started with and the molecular weight of that material. We can calculate how much Br is needed to do this reaction. Okay, so if we calculate the number of moles of HBr right here, then we can use that fact that it's 3 molar HBr to calculate the volume in liters of HBr that is required. So that is what we're doing there. We're calculating the volume that's required based on that 3 molar solution, moles per liter. Okay, so we're starting with grams of material and calculating the volume of a solution that needs to be added based on its molarity. Okay, now after that reaction is complete, you'll evaporate everything off and you'll be left with NABR. You have an amount of NABR that you think you should be forming, and you can calculate that based on how much of that Na2CO3 you start with. That gives you your theoretical yield for NABR. The actual yield that you measure will be calculated as that actual yield divided by the theoretical yield times 100%. So the percent yield has a different calculation than percent error, but they both involve actual and theoretical. Okay, so this one is actual over theoretical times 100. When we do a percent error, then we look at the difference between the actual and the theoretical and divide that by the theoretical times 100. Okay. So there is a difference in what we're doing there. Now this walks you through what would physically be done to make this happen. And what we've done is put together this little solution. So we take our weak base, we add a strong acid to it, we make salt, the NaBr, that we're going to collect, water and CO2 gas. Okay. Now, because we need to make sure that we've gotten this all the way over, okay, we put some methyl red indicator, which is yellow in basic solution and red in acidic solutions. So we initially add the Na2CO3, we add the methyl red, we add some water to it, and that's a yellow solution. Okay. We add the acid, the amount that we think we're supposed to use to do this. We make H2CO3, okay, and that gives us this red color. So it goes from yellow to red because of the formation of the H2CO3, okay? So that's done over a steam bath with a watch glass cover, okay? And we don't want to boil off the water that's formed, all right? But we do want to drive off the CO2, okay? So we get rid of that CO2. So as the solution heats up, the carbonic acid breaks down, forms water and carbon dioxide gas, pH continues to rise, and the CO2 leaves the solution. Okay. Then we remove it from the steam bath, because what actually happens is it goes back to yellow when we do this in the lab. We know that we've taken all of the CO2 out. We make it because it goes back to yellow. Okay. We remove it from the steam bath. We add some more acid to react with any residual Na2CO3 and do the steam bath again just to make sure that we've got everything. And we continue slowly then to heat the water. If we do it too fast, what happens is that if you heat this way too fast, the water that's in there suddenly evaporates. So it turns to steam and it explodes everything out. So any solid that's sitting around it blows out of there and it's kind of a mess and you lose that product. So you lose that mass and that's a loss that we would then have to discuss as a potential source of error in our laboratory. Okay, we take that NABR, we get it off of there and we weigh that. Okay, now things that are new in this lab that we've just started talking about: molarity, moles per liter, concentration. Okay, we've talked about spectator ions, those that don't actually perform any function in the lab that we're talking about. They're just there to balance the charge. Okay, if we start with 2.45 grams of sodium carbonate, it's treated with excess hydrochloric acid, how many grams of sodium chloride will theoretically be produced? So we're doing a theoretical calculation based on the amount of Na2CO3 that we started with. So that 2.45 is converted to moles of Na2CO3. We then convert from there to moles of NaCl and then multiply that by the mass so that we can get a theoretical mass that should be produced, 2.70 grams. But we actually only collect 1.54 grams. So we look at our actual yield, or our percent yield, which is actual over theoretical times 100, and that gives me 57.0%. So that's the example calculation of that percent yield. Okay, so that's the calculation that you're looking at there. We have similar things that we can look at for this, talking about how we convert from Na2CO3 and the HBr that we've added to get the theoretical yield of the NABR, okay? And of course, calculating how much HBr is required. So you may be asked how much HBr is required for this reaction, and that's based on this calculation right here, okay? Now the amount that you're given in the lab final probably won't be the same mass, so you can't just memorize the calculation. You need to think through the logic. So grams to moles of something else, to liters of something. Okay, so that's what you're doing there. You can then calculate your theoretical yield for how much NABR is supposed to be formed, and then eventually you can calculate a percent yield based on what is actually made. They may give you that information. When we talk about the net ionic reaction for this, the only things that are involved are the Na and the Br. The CO3, 2- is not important, the H+ is not important, because they just stay, okay? The H2CO3 becomes H2O and CO2, yes, okay, and that is true, but that is not part of the reaction that we're concerned about. It's a separate reaction. So we may have multiple things going on, multiple chemistries that we might be interested in, but that is not the one that we're concerned about at this point, okay? So the net ionic here is the formation of the NABR, and at the same time, we have this making the H2CO3, which spontaneously decomposes to H2O and CO2. Okay, so those are the two reactions that we're seeing in there. Now, again, since the chemistry that I'm actually interested in measuring and talking about is making that NABR, that's where I'm going to focus. The rest of it happens. We could collect the CO2. We could try and collect the water. There are lots of different things that we can do here. But what I care about is the formation of that NABR. Okay, so there's that. I would also recommend that you read through all of this stuff that's here so that you can see where there might be some calculations that you need to do, things that you might need to be concerned about. Okay, now the post lab that goes with this particular experiment is designed to ask you some of those questions that you might see on the lab file. That's what the post labs are for. Okay, so it's based on what you have observed in the virtual laboratory. So if I want to see that virtual laboratory, I need to come in and look at the synthesis of calcium carbonate. Okay, this is the synthesis reaction we're going to be looking at. So I'm going to open this, And say, okay, let's see what we got. So precipitation reactions are double displacement reactions, formation of an insoluble solid. You can read all of this stuff when you do your own. Know that Na2CO3 is Na plus and CO3 minus. Calcium chloride is calcium and chlorine. And of course, Ca plus CO3 becomes CaCO3. Okay. And we can find the moles of solute by multiplying the volume of solution times the molarity. Okay. And of course, if you want to get to mass from that, you can use moles times molar mass. Okay? We're using suction filtration, vacuum filtration to remove all of the liquid that we don't want. That's one of the techniques that we're going to be looking at. And that is something that we use in the laboratory to make sure that we've got it as dry as possible. So let's go see our simulation. In this experiment, you'll be mixing aqueous solutions and sodium carbonate to produce solid. Order the steps required to predict the volume, okay, of 1 molar sodium carbonate needed to produce 1 gram of calcium carbonate. There is an excess of calcium chloride. Okay, so I have a mass of calcium carbonate that I want to use. So moles of calcium carbonate. It told me how much sodium carbonate. I need to then convert the volumes, do that, and do that. Oh, oops, I skipped a question. Calculator. Dun, dun, dun. Jeez. Okay. So use your graduated cylinder to transfer approximately 100 mils of 0.1 molar aqueous sodium carbonate to the clean bead. Okay, fine. So the graduated cylinder is here. I want to take one of these happy. Sodium carbonate, put that in there, put that down. I zoom in, and I see that not 100, 95, 96, 97, 98, 99, exactly at 99. So in my lab data, I'm going to say 99.0. Okay. I zoom back out. This clean graduated cylinder to transfer approximately 100 mils of this guy. Put that in the beaker. Okay. Clean. Put that in there. Put that down. You zoom in. That is exactly 100. And then zoom out. And I need to close this. Both of those are labeled as 0.1. It is very important that you check the bottles because even though you think you know what they're supposed to be, they may not be. So that's why we have a space in our lab notebooks for recording that. How many? 10. Okay. Just want to make sure I wrote it down right. Because I'll complain if I don't. Okay. So I'm going to tear this. I'm going to put a piece of filter paper. I have to add this. Sorry. And then put that in there. I'm going to use heat it up. Hooray! Made a solid. So pair our balance. Use the forceps to pick one of those up and put it on there. That's 0.21 grams. 0.21. And then close that up. We pick up our guy and put it in there. We need to make sure we get it. We need to put that down. We need to make sure that we get it wet after we turn it on. So that's what that's for. If we don't get it wet, it flies around and doesn't stick where it's supposed to be. Pick this up, pour that in there. Set this down, pick up. Go on. Pick up one of these. And we'll try and get all out. It is very important to try and get all of it out. That is kind of a pain in the neck. And put that there. And then we rinse that again. And put that there. Turn off the vacuum. Use forceps to remove paper. Place it on the watch glass. There. Place a watch glass and filter paper with precipitate into the oven. Turn on the oven. Heat it for 10 minutes. Remove our sample and let it cool. And then we lay our filter paper. And you see right now it's 2.48 grams. 2.48. Okay. So I close that. I take this, I put it back on there, set that down, and put this back in the oven. Close it up, turn it on, let it heat. Now I get questions, why do I have to do this? Why do I have to do this? Why do I have to do this? Well, let's see. Let's see what happens if I do this. Pick this back up and I put it back on there. 1.72 grams. Oh dear Lord, that's a pretty big difference. I had 2.48. The reason I have to keep doing this is because I may not have gotten it dry enough the first time. So I have to keep checking it. And the way that I keep checking it is by continuing to put it into the oven. So I put it back in the oven and I heat it again and let it cool again. And I weigh it again, 1.30. You see that that mass keeps changing. Pick it up again, put it back in there again, put that down, pick that up, put that in there, turn it on. So I need to make sure that that is a constant mass. So this is why I keep doing this. It says, repeat steps 3 to 6 until sample reaches a constant mass. So that's what I'm trying to do, is get it to that constant mass. That's 1.5. And you may notice that I am recording everything in that spot, no matter what. And I always do it before I go move to the next thing. It is really important that we are keeping an accurate log of what we're doing. If this were my lab notebook, I'd have several lines where I had recorded all of those pieces of data and not written over them, because it's important that we record all of them. I like to see how many times I had to weigh it to make sure that it came to a constant mass. I want to see that it was actually a constant mass. So that's pieces of information that I may need. If this reaction is going to be done by somebody else, they may need a better estimate of the amount of time that it should stay in the oven. So if you did it 4 times, which we did, then they might want to put it in for 40 minutes. Now notice, 1.05, 1.05, so we're good. Okay. In lab data, calculate the mass of calcium carbonate that was collected. Okay, so how would I do that? That's a mass by difference. So I take that mass that I ended with, and I subtract the one that I started with, and that's the number that I need to record. What is my limiting reagent in doing this? Let's see. What was my limiting reagent? Well, actually, based on the volumes that I have, I'd say it's sodium carbonate. I'm not going to tell you why I think that, because it may not be the same for you. Now, the expected mass I can calculate. Again, I didn't watch through any of those calculations. My expectation is that you can figure out how to do them. If you cannot figure out how to do them, then we need to talk about that. If you need any help figuring out how to level and read that the volumetric flask, we need to talk about that. So any of those things we may need to talk about. So that is what you need to do for that. I am not going to walk through any of the post lab because that's on you. So you have two chances. If you mess it up the first time, talk to me about it. And we can talk about what are the issues that you might have been seeing in doing that. So that way you can go into it better prepared the next time. Okay? I'm going to share my screen and I will talk to you guys again soon. Thanks.